Next up now is Thomas Grant from Cegal. I'll share now, Thomas, so you can be the organizer and present. While you do that, I'll say just a few words about the title and what we're going to do. So we have used machine learning with Python and also using this to scale it into our GeoCloud solution on Azure. And Thomas will give us half an hour highlight on how we have done that. So feel free to start when you see your other screen. Just there you go. Come on, Thomas, you're ready to go and unmute.
Good afternoon, everybody. My name's Thomas Grant. I'm a senior geologist working at Cegal. My background is in geology and geochemistry. I also have some experience working in the finance industry. And since joining Cegal, I've been working in a number of different data science related and digitalization projects. I've been predominantly coding in Python as well as SQL. And today I want to talk to you about some machine learning, which we're going to do using Python language. I'm also going to be using a number of services available through Azure and have a deployable product that can be deployed through GeoCloud, whether that's GeoCloud on-prem or GeoCloud on Azure. So I just want to give you a little bit of background here. The state of technology over the last years has shown really rapid advancements in things like computing power. This makes AI and machine learning much more available. We've seen rapid advancements in not just the capabilities of artificial intelligence and machine learning, but also things like the accuracy and the ease of use and implementation in our everyday lives. So now it's possible to go from a completely new algorithm from research to actually being implemented and deployed and in solutions that affect many, potentially millions of people. Also seeing rapid advancements in things like analytics or analytical solutions. There are a number of different ways you can build dashboards and reports based on your data, and advancements in storage of data. And all of this is combining together. And this is a rapid set of development to try and keep pace with the amount of data that's starting to appear in the world. All types of data are increasing exponentially in the world, and in order to account for this, this is why there's such a huge space here for development. I've given just a snapshot of a number of different solutions available out there, different programming languages, databases, visualization tools, and so on. The space here is extremely crowded and also ever expanding. So it can be quite a wilderness out there on what to choose, what do I do, which language is best for this solution, what can I use. So one of the things that we do in Cegal is we try to innovate and explore some of this space and develop tools that combine potentially different languages or different software solutions out there, and for example cloud services to solve real world business problems. And what I want to talk to you today is unstructured data. So I went looking for a quote to find out roughly how much unstructured data there is out there. As I said, generally data is increasing exponentially. Most quotes come around with a similar figure. So I just took this one from IBM, which says it's estimated that 80% of the world's data is unstructured. But businesses are unable to gain visibility into a portion of that data. Now, what do we mean by unstructured? Unstructured data is data that has no schema, it has no regular structure. It may contain different data types and be from different data files. And this lack of structure makes it rather difficult to combine, store, and use that data. One of the main file type I'll be talking about today is PDF formats. And I think we can all relate to this problem because, for example, each employee in a large company may have access to or work with a limited set of PDFs, whereas the company may have tens, if not hundreds of thousands of PDFs stored across many different drives. And how do you make that data locked inside those PDFs more visible and usable to different employees or all employees. So as we are EMP focused, particularly today, I'm going to talk through a workflow and a potential solution for dealing with unstructured data in the EMP industry. Let's imagine you have your geoscientist or domain expert sitting there. They're interested in looking at, say, drill reports. This may contain a whole variety of images, text data, and even some tabular data. They may even receive vendor data in the form of PDF reports, and these could be, although similar data from one vendor to another, the structure is totally different. They may also want to implement brand new research or even old research into their current project. For example, they might be wanting to be collating data from decades of research from different research papers, which have totally different formats, and be able to combine them into some sort of data that they can then use and put their own data in context. Finally, there could be internal reports, for example, synthesis of ideas and work done within a company on certain projects that can get put into PDFs and put away. So you may be able to read some of these or access them or find them, but often in order to access information, it's still locked inside that PDF, and you've kind of either got to know which PDF that is, what drive it's stored on. That can lead to asking someone, hey, where is this data? Where can I access it? And as a visual metaphor here, this person is quickly towered by all these different types of PDF formats, and how they want to be able to use that data is a particular challenge. So in steps in our summer project over this last summer called Project SPUTNIK. The idea was to make some sort of PDF management solution that is compatible with OSDU. We had a fantastic summer student in Bendik Skarpnes who came to work with us. There was Tora Ordland, a software developer in the digitalization team involved, and as well as myself, also partly in the project. A workflow was quickly drawn up just to illustrate the problem and how we might tackle this. Envisage a data manager who has a PDF that they want to upload to OSDU and have it properly stored, and then be able to access this later on. But this document, this PDF document, is going to pass through whatever we make inside Project SPUTNIK. That is going to, and inside Project SPUTNIK, we're going to be extracting data and information from that PDF before it's then stored in OSDU. Our end user is going to be a geoscientist or any other domain expert. And again, this could easily apply to any other industry, something other than EMP industry. And this domain expert, this geoscientist, is not only going to be able to search for a document, but be able to search within a document for the data they want to look at. Then we had to decide on the technology stack. And as I said before, there's a huge amount of options here for us. One of the first principles that we talked about was being able to leverage open source existing code, particularly that coming from new research. So we went and we found this excellent project from University of Wisconsin. This was open source project for being able to fragment PDFs into their different pages and images and text and so on. We wanted to customize this, particularly for the EMP industry, and implement some of our own machine learning using Keras and TensorFlow to develop our own image classifier. And then to create a simple user interface where not only we could test everything that we're building was working, but also that could be worked on and deployed later on. And so we chose Cegal Data Labs or Cegal Labs. And all these combined are predominantly using some Python, which is excellent because Bendik, Tor, and myself, as a common programming language, all know and are proficient in Python. Then we looked to using some public cloud services. Most different public clouds have fairly comparable offerings on different types, but we wanted to use some cognitive services that we could quickly pull out the box to do some more extra work, so we could work a little bit faster. We're also going to be developing a data pipeline, so we need something to hold this pipeline together and automate some of the tasks and communicate between different blocks in that architecture. And finally, we needed some sort of database solution to store the data and make it accessible and searchable. So I'll go into a little bit more detail of all of these different things we have in our technology stack. So this University of Wisconsin's Cosmos project, as they describe it, is an automated dark data extraction and knowledge-based construction from scientific publications. This enables the extraction of fragments, i.e. figures, captions, text, and tables, from PDFs, to then make them searchable. So it stores the data of not only what the PDF was, what the page is, and also the fragment number that it's pulled out. So this has got us a long way already, and we're able to use this because it was open source. However, once we've extracted images from these PDFs, and bear in mind that this open source code was largely for research papers, we need to customize this for the EMP industry. So the types of images that we're going to be pulling out from the PDFs that we want to look at are going to be geo-related images. We identified a number of different geo classes, things like maps, thin sections, rows diagrams, 3D block diagrams, and so on, that are likely to come up. And this is a pretty extensive list of what you're likely to see. And of course, we had to add in an extra class of something that is not a geological image. So just as an example, we've got a picture of a cat. I think you're unlikely to see a cat in one of your drill reports, but you never know, you're going to see something that may be not geologically related, and we need to be able to filter that out. Starting with a very good performing neural network for image classification called MobileNet V2. This was developed recently in the last few years by Google, and this provides not only comparable, if not sometimes better accuracy than a number of other image classifiers. This was actually designed to run on mobile devices or other devices with limited computing power, so it's also pretty saving us some computing costs here. This MobileNet V2 was originally trained on the ImageNet database. And what Bendit did was he chopped off the top of this to set the output layers in order to have the right number of outputs to identify our 15 classes. That's our 14 geoclasses and our non-geo class. And then it was retrained on an image database that we were able to obtain. It doesn't mean we always want to be programming things from scratch or necessarily programming everything. We can actually link into a number of cognitive and AI services that are available to us through the cloud. So we can use some of Azure's cognitive services. What these are is a comprehensive family of AI services and cognitive APIs to help you build intelligent apps. Cognitive services brings AI within reach of every developer without necessarily requiring machine learning expertise. What this means is it doesn't mean you don't need to know anything about machine learning. It just doesn't mean you don't have to reinvent the wheel every single time you want to build an app. So you can go through rapid, fast development and bring in a number of cognitive services where you need them. And if you feel like they need customizing, yes, you can go into that level of detail, but it's about quick rollout and quick solving of solutions, solving of problems with new solutions. Just to give you an overview, this family of AI cognitive services is pretty extensive. I haven't given a full list here, but just to give you an idea that they fall into a number of different categories. There are cognitive search services for things like decision-making, anomaly detectors, for example. For language, you have translators, text analytics, language understanding. For vision, as well as web searches, we can make customized searches, image searches, video searches, and even cognitive services for speech, such as speech to text, text to speech, speaker recognition, and speech translation. So it's a huge amount of services available at our fingertips to quickly develop what we're working on. Next, as I said, we're going to be creating a data pipeline. If you remember that workflow that I showed you earlier on, we're going to be extracting information from PDFs, and we need to automate some tasks here and have some communication between different stages of our pipeline. What's perfect for this is Azure Functions, and these are an event-driven serverless compute platform that can also solve complex orchestration problems like the one we're going to have. Azure Functions can operate at scale in the cloud and integrate services using triggers and bindings. So they'll recognize when something happens, they'll do this, it'll run through a function, and then we can move on to the next stage of our data pipeline. Finally, we wanted a place to store all of this data we're going to extract from our PDFs, and it needs to be accessible and searchable. Azure CosmosDB is Microsoft's globally distributed multi-model database service. By multimodal, we mean there are different APIs in order to interact with your data. Even though this is a schemaless NoSQL database, there is an SQL-like API in which you can search through documents. So it's quite easy for people who are familiar with relational databases to pick this up and start working with. You can also use a graph API, and so develop your own knowledge graph and create more deeper relationships between the data that you've extracted from your PDFs. CosmosDB also enables you to elastically and independently scale throughput and storage across any number of Azure regions worldwide. This means that you can put the data where the users are. So if you have a global company, which many EMP companies are, and for example, in other industries, that the data is quickly accessible. Finally, Hilda gave a fantastic presentation earlier on Cegal Data Lab, but I'll give you a quick refresh just in case you missed it. Cegal Data Labs is a centralized hub for collaborative data science and data management. It helps businesses create quick value by creating small MVPs that can solve the problems at hand. So this is just perfect for us. Again, we want to be working in Python because we all, the Bendik, Tor, and myself, are working in Python here. And we can do this inside Cegal Data Lab, and we can quickly develop a user interface to not only test the architecture, but then build on for potential later deployment. So I'm going to go through the architecture that was built inside Project SPUTNIK. It's fairly complicated, so I've broken it down into a series of stages, keeping with the same logos for each of the tools that we're using here. You start off with the data manager. They're going to have their PDF file. They upload that to blob storage. We have an Azure function that's going to recognize that there is a new PDF file inside blob storage, a new blob. And it's going to say, hey, we need to do something with this. It passes this to a queue. The new PDF is standing in that queue, waiting to be processed by our PDF processor. The PDF processor is a virtual machine that is GPU enabled. And inside here, this is where we run that open source code from University of Wisconsin. We need that GPU enabled, so this is fast and as efficient as possible. And then we also run our custom GeoImage classifier inside here. So we're extracting not only the fragments from the PDFs, but PDFs, such as whether it's a block of text or a caption or an image. We're also correctly classifying them as what they are, what type of image it is. We can also now pull in some of Azure's cognitive services, and we pull in Azure's OCR. This is optical character recognition, which will be able to pull out the text from any blocks of text that we've extracted from the PDFs. All this metadata, what the PDF is, what the page number is, what the fragment number is, and all of the information we've then extracted from that PDF is then going to sit in a queue, ready to be passed to our database. We also have all those fragments actually sent to blob storage as well, that we can access those later on. There's now a level where the data manager can QC, quality control, everything that's happened to make sure that this is done correctly before being passed on. That PDF can now be committed and stored inside OSDU along with its necessary metadata, so that we can always go back to that original PDF and it's stored correctly. All of that metadata we extracted from the PDFs are sitting in the queues here, ready to be uploaded into a database. And so we have an Azure function that's going to be able to do that for us. It's going to recognize that there's data stored in the queue, and it's going to correctly organize that into our databases. We set up one Cosmos database using the SQL API and one using the Graph API. So we were able to construct a simple knowledge graph here. Also able to pull in yet another one of Azure's cognitive services, Azure Search, to help enable us have relevant searches when our end user is looking for the data they need. The final stage is we can combine this Azure Search, the search to OSDU where the original PDF is, and both our Cosmos databases into a federated search, again, an Azure function. And then we can pass that to the end user who's going to be working inside Cegal Data Lab. So all this is kind of hidden behind in the back end where the end user doesn't necessarily see, and they can quickly search this database for the information that they want. So I can give you a quick demonstration here. And we can go into Cegal Data Lab. I hope everyone can see me now inside Cegal Data Lab. I signed in using Keystone. I've navigated to the folder and the Jupyter notebook that we want to look at. We have a simple set of widgets here where we can enter a search criteria. I'm going to search for the word Cretaceous in a number of PDFs that we have extracted data from and uploaded to this database. So we worked with a handful of PDF files that were open source and able to download from the internet. So we search and we start producing some results, finding some images, and we start getting some returns on what we're looking for. So we're finding stuff that contains the word Cretaceous. We have some text here containing Cretaceous and a number of images from PDFs relating to the Cretaceous period. Now I could also say, let's do a slightly different search. Let's look for permeability, and we're going to look in tables. I want to find some permeability data. Just need to clear my log here. And we search, we get a nice little data table with some permeability. And you can see here we've got the fragment ID. This is the ID relating to what fragment this was, the page ID, what page it was from, and what PDF file this was taken. It's correctly identified as a table in our geoclasses, and we have the OCR pulling out the data that we want to look at. I now move back to presentation and just give you a quick summary. So what we've managed to achieve in what was an extremely short space of time, this was just over a month, we managed to do all of this work. We leveraged open source system for parsing and cracking PDFs. We adapted this for EMP documents to correctly classify geo images. And we used some of Azure's cloud services to quickly develop a data pipeline and database to access the data extracted from those PDFs. We used Cegal Data Lab to make a quick user interface to be able to search that database, not only to QC this process, but also as a basis for further development of the user interface that's quickly deployable. We found that this was an extremely highly effective way of working. We were able to rapidly, in just a number of weeks, develop some custom solution that can solve a real world problem. I want to quickly hand you over to James Goldwater, who has a little to say.
Hi, hope everybody can hear me. My name is James Goldwater, and I'm a senior developer here at Cegal with 20 years experience. I've been involved in many of the things we're presenting today, although not really with what Thomas has just been showing you. And I wanted to say something a bit more informal about what we've just seen. When I saw this system at a small presentation a couple of months ago, I was astonished. Because although I work hard to keep up to date, seeing a system like this developed made me realize how far we've come. Petrel and similar apps like RMS were first released about 25 years ago, and in that time they've become prettier, bigger, probably slower, and with many more geoscience capabilities. But if you were to travel back in time, you'd recognize them. They've fundamentally not changed at all. They're still a desktop system running on a single thread, working on data on your computer. They've got a tree to the left and a 3D view on the right. This system Thomas has just presented is different. First, the capabilities. 25 years ago, this system would have involved multiple PhDs of work as well as a huge development team, and it would not be nearly as good. We were able to take an existing machine learning model and train it to classify geoscience images in under a day on a laptop. It's inherently scalable, as it's based on serverless functions which run in the cloud. So we can throw more data at it and expect it to just naturally work. And the speed at which we developed it, 1 month, involving a student and a developer. We need a database. We spin a managed database up in Azure in 5 minutes. A state-of-the-art optical character recognition engine. Add a call to Azure Cognitive Services. 3 lines of code. And finally, it's cost. There are commercial services which do similar things, but they take weeks to process data and cost a fortune. And we estimate that the pure compute cost of this solution is 2 orders of magnitude lower. Now, of course, this is not a commercial quality service, but not everything has to be. This system and systems developed like it are obviously not suitable for deploying to 20,000 seats worldwide initially. But there could be real business value deploying it securely to a small number of expert users in different asset teams. And this is where something like Cegal Innovation Space comes in. Without it, the jump from research code on a laptop to an MVP is much harder. because you have to commission and configure servers to host it. You need to add authentication and security, and then you have to go through IT change procedures to connect up databases and storage. With something like the innovation space, all of that is pre-configured. Developers can deploy onto the Kubernetes cluster using Docker images, which means no compatibility or versioning headaches, and then use Cegal Keystone authentication to make it available to sets of users quickly and painlessly. And then, if the business finds this valuable, they can continue to invest in the system and deploy updates at whatever cadence they want, monthly or even daily, in a very simple fashion. Well, that's pretty much all I wanted to say, but to summarize, your people, using modern development ecosystems can do amazing things nowadays, more quickly and cheaply than you can believe. And we want to allow it to be easy to turn this into value to the business and make it accessible to your users. That's all I had to say, so back to Thomas and Stoffer.
Okay, thank you very much for listening, and thank you, James, for your comments. And yeah, also thanks to Bendik and Tora for their fantastic work on this project.